Hello, this is Lou Feijs. Again, we are at Eindhoven University of Technology, and this is the third lesson in this course, Golden Ratio. Today we're going to go somewhat deeper. We're going to deploy calculus, and you will see that it really works and is practical at the same time. Here you see the resources for today's lecture, the PowerPoint, the programs I made, and an external link about a curve called the cardioid. Some inspiration: the cardioid is a very beautiful curve, and like in medicine, cardio means the human heart. And here you see the website of Francesco de Comité. He makes fantastic 3D printed forms based on this mathematical curve called the cardioid. Here we see the website of Gabriela Ligenza, a milliner, that means a hat maker in London, and he has based 3D printed hats on these cardioids designed by the same Francesco de Comité. This is the plan for today's lecture. As before, I will show you where these curves happen in nature. Then we go somewhat deeper into the mathematics of cardioids, and we will also deploy some calculus so we can talk about tangents, for example. The formulas can go into a processing program which I will develop as we go, and then I will develop an example where this is used in embroidery, and also a final example. That's why I brought the laptop. There will be also a dynamic example with a sensor. Where do we find these hard curves in nature? As you see, I write here nature in quote because you won't find them when you walk in the forests or along the beaches, but you will find them in the man-made new nature which we encounter today. For example, in coffee cups. Here you see a coffee cup. It's my own coffee cup, and when the light shines in it from the side, this is a conical cup, there will be this light effect at the bottom of your cup. Here you see it, and it has always this typical form which we call a cardioid. Here you see another example in using and designing microphones. Microphones have a directionality. They want to pick up the sound from the speaker, and in particular they also want to cancel out noise which is coming from the wrong side. So here you see a kind of polar plot giving the directions, and you see the directionality of it. Again, the same typical form. You also encounter them in the nature of mathematics itself. Around 1980, Benoit Mandelbrot, you see him here in the picture, discovered that a fairly simple formula, z becomes c squared plus c. You can try to iterate this process, and then depending on the c, this will stop or will not stop. And what you see is that this gives rise, if you investigate for which values of c this works, it gives rise to this very typical form which is called the Mandelbrot set, and it's one of the cornerstones of modern chaos theory. And again, the main curve of this shape is this cardioid. The mathematics of the cardioids, you see there will be a coordinate grid again, and I will later explain that on the light board. I will talk about the geometry, the characteristic heart shape, the equations, the polar equation, parametric equations, and as you know, for programming I prefer the parametric equation. And then I will also deploy a bit of calculus for finding tangents, normals, and talking about the speed when you draw the curve. Here you see it again, the coordinate system and the cardioid. Question is, what are the equations which describe this shape? That's what I'm going to do at the light board. Now I would like to discuss the equations of the cardioid, and As a kind of reference, I'd like to make an easy start by looking at the equation of the circle again. You know, the definition of a circle is that any radius r has the same length independent of the direction. So this is the basic principle of a circle. R is constant. In polar coordinates, this is extremely obvious. If we go to Cartesian coordinates, where we like to know points x and y in numbers, x and y, so we assume a coordinate grid, this being the x, that being the y. Then you know how that works, namely x equals the cosine of an angle theta times r, and y equals the sine of theta times r. And then theta is an angle which goes like this, which means we can draw the circle by incrementing this theta in small steps. So if I want to draw this circle in a processing program or any other language, I would consider this theta to be the same as time. So I would introduce time as being essentially the same as this theta, which means I would create programs like a for loop for t being initialized at 0, proceeding until t less than 2 pi, and t being incremented in small steps, say dt. If I do that, then this whole x, y calculations, they go inside the for loop, and we can think of t as a time parameter because the for loop increments that in steps of equal size. So this is the circle. You knew that, I guess. So now this cardioid, if you want to make this cardioid, it has this typical shape like this, and in the equations the coordinate system will be aligned like this. So it looks a bit like a circle, except for the fact that if you look at the radius here is very small. At this point it's even 0. Here we have a much larger radius. So that's the idea which gives us an equation. Here the radius is 0 in that direction. For an angle of 90 degrees, we take an r being 1. Here we want to have an r equal 2. Here it's 1 again. And it turns out that in order to get this type of radius, there is a very simple formula, namely take the radius to be 1 minus the cosine of t. Perhaps you still recall how the cosine works. The cosine of 0 is 1. The cosine of 90 degrees, pi divided by 2, that's 0. Cosine of pi equals even minus 1. And then it turns back to 0 and to 1 again. So you can check 1 minus 1 equals 0, that's what we need. 1 minus 0 equals 1, that's what we need. So in this way, if we take this r, we will have a formula for the cardioid. So let me write down the equation for the cardioid now, because that was what I was after. Equation, the x equals cosine t times 1 minus cosine t. See, this is the r, and part of that is the same formula we had for the circle. And the y equals the sine of t times 1 minus the cosine of t. And these two equations together, they describe the cardioid, and it's a parametric equation, so the t is the parameter, and whenever I fill in the value of t, I get a x and a y, so the same for loop will draw a cardioid now. Next, I would like to do a little bit of calculus to show the calculus in action, but also because I want to be able to calculate the tangents to this figure. So if we have the cardioid here, like this, the question is, at a certain point x, y, what is the tangent? So you know the tangent, it's a line like this. It has one point in common, but not more than 1 point. So it just touches the curve. And you know the theory of differentiation there. The idea is that you make a small step in the x direction, which they call the x, and then the question is, what is the step in the dy direction? And the dy dx, the ratio between the two, that is the slope. In order to find that slope from the equations, we're going to use some calculus, and in particular we will be using the following formula, namely that the dy dx is obtained as the dy dt, so taking the derivative of y, t being the variable, divided by dx dt. You would guess that this is fairly logical, because if you do this with number like 7/3, it's the same as 7 divided by 50 divided by 3/50. You just can cancel out these common factors. Here it's a rather deep theorem of calculus, but it's easy to remember because as it happens, it works out in the same way as this simple arithmetic. So now the next task is to find these derivatives, the derivative of x, the derivative of y. So we have to take the derivative of these formulas. I hope you had some calculus before, otherwise I will summarize the essence. Namely, if you take a cosine function and you want to know the derivative of that, so I also indicate that with a quote, then as it happens, the derivative of the cosine is the sine, but you have to add a minus sign. The derivative of the sine equals the cosine. No further sign needed. So just to make sure, this quote notation, that's the same as writing d dt, so taking the derivative regarding t. Here we have cosines and sines, so now we know how to take those derivatives. One tricky thing is we have a multiplication here, so we have the cosine t multiplied by this thing between brackets. Taking the derivatives of something with a multiplication in it, in general say ab, and you want to have the derivative of that, you have to work in two steps. Namely, first you take the derivative of a, but you don't touch the b, and next you don't touch the a, but you take the derivative of b. And those things can be added up. So this is a summary of calculus. That's all we need to know here. And the trick is that we calculate those slopes by doing this symbolic manipulation. That's what Newton invented. In order to make those, to find those slopes, you have a kind of substitution on the formulas. You replace the cosine with a sine and you add a minus sign. And in that way you get new formulas describing those slopes. if we have those slopes, we can plug them in this formula, and then we really know the tangent. So let me summarize what we have seen so far, namely the x equals cosine t times 1 minus cosine t, and the y equals similar formula, but then we have a sine. And now I would like to know the derivative of the x, and I would like to know the derivative of the y. So here we're going to apply the product rule. First we do the x. So this is like the a times b. First you take the derivative of the a, it's this one, not touching that one, and then the other way around, not touching the cosine, but taking the derivative of this. So finding the derivative of x, t being the variable, we first take the derivative of cosine t, which is the sine t, but I add a minus sign, and I do not touch the part between the brackets. And then I have to add the same thing the other way around. I do not touch the cosine, but I take the derivative of the 1 minus cosine. The derivative of 1 is 0, so I forget of that. I take the derivative of minus the cosine, that's the sine again, but I have to add a minus sign, and actually there is already a minus sign, so that cancels out. And if I clean up this, these pieces, I find that it's minus sinus t plus 2 times cosinus sinus. I can do the same for the y. So the y prime is taking the derivative of the sine, that's the cosine. I do not touch the second part, non ci tocca, as the Italians say. And now the other way around, not touching the sine, and taking the derivative of 1 minus cosine. It goes the same again, that's the sine, the two minus signs cancel out. So if I summarize this, I find that it's cosine t plus a double sinus t minus a double cosinus of t. If I have these formulas, I can just copy them into any programming language which will numerically evaluate that, and then I can find the slope. As earlier I wrote it like dy dt divided by dx dt. Using the prime notation, it's y prime divided by x prime. So that means that if you go a certain step dx in this direction, you go a certain step dy in that direction, and then this is the slope. Using the same calculation, I'm well positioned to also find the orthogonal, so the line which is orthogonal to this slope. Sometimes we call it the orthonormal, but normal assumes that we compensate the length, so it's 1. Then we call this line a normal. So what's the slope of this orthogonal direction? Well, if we have the y prime and the x prime, the orthogonal direction is easy as well. It's just the inverse of it, so it's not the y prime over the x prime, it's the x prime over the y prime, and I add a minus sign. So what you see here, it makes a small step upward and a big step to the right. Here it's the opposite. It makes a small step to the left and a big step upward. So that makes this formula plausible, and now I also know the direction of this orthogonal line. So this is why these derivatives are useful. It works by symbolic manipulation. You massage the formulas with some substitutions, but then you get numerical values which can be used for drawing tangents. There is another practical usage of these formula, namely that's the notion of speed. I told you already that the t works like time, and then if we are drawing a curve like the cardioid or other curves in a certain step, time step t, you travel along the path, perhaps traveling in this direction, it depends, and then you travel along the path, we call that ds. We work in this same style with dx and dy, so we travel a short path along these curves, and we want to know how long this is. Well, if we put the dx here and the dy there, we get a small triangle, a triangle of the orthogonal type, which means that Pythagoras' law applies. And actually, the Pythagoras law doesn't only apply here to this triangle, so the ds squared equals the dx squared and the dy squared. It also works at the level of the derivatives. So I like to present you this impressive but very powerful formula, namely the speed, that is the rate of change along the path as a function of time. That's given by a kind of Pythagoras formula where you use the dy dt and the dx dt. And in this way you know how fast it travels along the path, which is interesting when approximating a path by dots or things like that. Then it's about the distance between the dots. It's also interesting if you work with a machine like a 3D printer or a laser cut head. Then you're also talking about the speed this machine is making. And using this formula, we can calculate the speed. And inside the formula, we have the same derivatives I calculated here in green. Next step is to make a processing program where we put all this theory into practice. Next, we're going to do some coding in processing, and this is where the formulas which I derived will come in handy. This is the basic idea. We will divide the full circle of 2 pi in steps, small steps, which we call dt, which is like 2 pi divided by the number of steps. We'll use the parametric equations, and then we will find the points x, y in a single for loop, incrementing the parameter t in small steps dt. We'll also calculate the derivatives, the derivative of y in respect to t and the derivative of x, and using these we can draw the tangents and the normals. And I will play with these in search of something which is aesthetically interesting and which can be made in practice. Here we see the main function which is going to draw a cardioid at center coordinates xc and yc, and there is a parameter a which determines the scaling of the whole cardioid. This one will do 100 steps, and you see the main for loop where t is being increments in small steps, and it looks very much like the equation of the circle and the ellipse which we have seen before. X is this offset xc plus a times the cosine, and y a times the sine, but we have this extra factor 1 minus cosine, which gives rise to the typical cardioid shape. If you don't know where to find such equations, look at this Wolfram MathWorld website, look for the parametric equation, and then you can copy them into the processing program. In this case, we are going to approach the ellipse by small dots. So you see the processing command called ellipse that is making small circles with a point size of 10. And the main draw program is going to draw the cardioid slightly to the right of the center of the screen, a cardioid with an A parameter of 250. Here you see the outcome of this, so these are 100 steps. You see this produces the cardioid approximated by small circles, and now we will deploy the calculus to make variations of this works towards something which we can implement. Of course, we can connect the dots and then we get the line. The program which is on the GitHub has all these features in it, so if you want just one of the features, you comment away some of the others. One question is, can we draw the tangents? Here you see a few of those tangents. They are the lines which touch the cardioid but do not go through it. And yes, we can. Here is the basic idea of drawing a line if you know the tangent by its slope. So suppose we have a point x, y, which touches the main figure. Then we can choose another x, say x plus 1000, so that's very far to the right. And then how much should we go up? Well, y plus 1000 times the slope. That's the definition of the slope. It's the ratio between going forward and going up. So in this case, if we go to x plus 1000 and y plus 1000 times the slope, then we get a tangent line. And how do we get the slope? Well, that's precisely why we took those derivatives. So now we see the same program again, the same main loop of the function cardioid, 100 steps, and we see we do not only calculate the x and the y with the same formulas as before, but we also have the formula for dx dt and dy dt, the two derivatives. The formulas look slightly more complicated. I've been deriving them on the whiteboard, but once you have them, you can copy them in here. In this point in the for loop, the t is known, so processing evaluates these to two numbers, and then you get the slope by dividing those two numbers, dy dt divided by dx dt. You don't only get the slope, you also get the orthogonal line, the normal which is orthogonal to the slope. You just flip the dx and the dy and you add a minus sign. So the slope is going like this, the normal is going in that direction. And you also see the line command which draws the tangent. If we do not show the dots, only the tangents, we get something like this. So actually the cardioid itself is not drawn. It appears as a gestalt from the tangents which go around it. Here we see how we will draw these normal lines. So when we don't want to have the tangents but the lines orthogonal to it, we have this slope of the orthogonal. And then we should change the length of that a little bit. So there is a deviation which we call dx. That determines the length of this normal. It's not 1000, it's a smaller number, say like 30. But we correct it a little bit depending on the tangent of this orthogonal slope, so they will all have the same length. And then you see the same, we draw a line from x minus dx to x plus dx, and then the y deviations, they're defined by this ortho. In the same way we had this number 1000 now, we have this number, this ortho now, which has been corrected. If you do that, you see we get these orthogonals in the same way they suggest the cardioid, but actually they are lines perpendicular to the line itself. Here we see also something else, namely that the distance between those lines is not the same. Closer to the pointy center of the heart, they are very close to each other, whereas at the far end, they are quite remote. This is where this notion of speed comes in. If I'd like to correct this, so that's the question, how to correct for that, we need this notion of speed. Here you see that in the program is essentially as before, calculating x and y, the derivatives, dx dt, dy dt, then we get a slope, the orthogonal direction. And here you see the speed. The speed is like a kind of Pythagoras formula working on the dx dt and the dy dt. And this speed tells how fast you travel along the curve when you increment x. And what we can do is have a variable steps size. And with the variable step size, we will correct for this. So if you look at the second line where it says for float t becomes 0, t less than 2 pi, t incremented by dt, now it says t is incremented by dt divided by speed. So where normally the speed would be high, we take smaller steps, and where the speed would be low, we take larger step. And in that way, we automatically get equidistant sampling of the curve itself. So this is the one change. We have a kind of basic dt, which is as before. We have this calculation of the speed based on the Pythagoras formula of the two derivatives. And then we use that in this point in the for loop where we have a correction factor, so the speed is depending, the real speed is depending on this calculated speed, so that cancels out. Here you see the effect of this. So now we still have normals and they are all at the same distance. With a little bit of programming, I add something else. So now we have a positive dx and a negative dx, so we cross it, but we can also zigzag if we take the dx alternately positive and negative. So then we jump from one red dot to the other red dot. And here you see that I modulo 2 means counting like 0, 1, 0, 1. And the plus plus means that we increment the I every step, and then the dx flips sign. If we do that, we can connect them. We connect them by lines if we keep track of the previous x and y and the new x and y, and in this way the line command hops from one dot to the other dot, kind of zigzagging. The zigzagging, here you see this done by the program for 200 steps. So I call this super stitching because the parameters in the program can choose whether these are large deviations or small one, how many we have. But I also call it super stitching because this has been embroidered. So the sewing machine makes small stitches, but at a larger level we have these super stitches. So the next step is to embroider this. It can be done on a fully computerized embroidery machine, or in this case a traditional sewing machine. The pattern has been printed on paper, and now the machine follows the paper. Later the paper can be removed, and then we have it in cloth, soft thing, which can be used for all kind of creative next steps. I have it here, so I will show it to you here. This is precisely this pattern embroidered. You also see the advantage of this, namely we don't have this spiky point which tends to make a traditional heart narrow. We have lots of space here, And I will use it, here I have a photo of my wife, and I will pin it in here. This is nice. I think she's going to like it when I take this home this evening. So, before showing you the final demo, the recap and the reflection, so like many of those curves, you should be looking for the parametric equation. Calculus comes in handy here because now we can find slopes, tangents and normals. For example, if we calculate dy divided by x, we can have the derivative dy dt and divide that by dx dt. Calculus also gives us the speed along the path. ds dt is a kind of Pythagoras formula involving the two derivatives regarding to t. Of course, we use the PDF library, then processing produces vector graphics, which can be used for embroidery machines. As I showed you, you can make soft things or laser cutters for harder materials. Before going to the arriving at the end of this session, I also want to show you another demo. This little installation has a heart sensor. So when I put this heart sensor on my finger, it will detect my heart beat. And you see here this processing program which gets the heartbeat from the sensor. And at every beat, it makes a series of cardioids of varying size showing my heartbeat. This is an example of an embedded system, and also there this type of mathematics comes in handy. That's it for today. Thank you very much for your attention.